Welcome to the Aerospace Ambition podcast. I'm Marius, your host, and an engineer passionate about the intersection of sustainable aviation and AI. In this episode, we'll talk about the aspect of weather prediction in the context of contrail management. We have two distinguished guests from the German Weather Service, or DWD, who are experts in meteorology and its applications in aviation and climate science. First, we have Dr. Carmen Emmel. Carmen holds a PhD in atmospheric science and has spent a decade in atmospheric research and forecasting. For the past 5 years, she has been with the DWD, where she coordinates meteorological aircraft-based observations. She is a prominent expert in aircraft-based observations, contributing to several EUMETNET and WMO committees, particularly focusing on humidity measurements. Carmen also serves as the vice chair of the World Meteorological Organization's experts team on aircraft-based observations and leads the subgroup on water vapor measurements. Joining her is Dr. Björn-Rüdiger Beckmann, a senior aviation meteorology expert at DWD. His career spans over 2 decades at DWD, beginning as a weather forecaster and moving into aeronautical meteorology. He focuses on commercial aviation, climate change impacts on aviation, and climate change mitigation. Björn has also contributed to the European Met community and works with various organizations on climate-optimized flying and aviation safety. Carmen, Björn, welcome to the show.
Thank you for having us.
Yes, thank you very much.
It's great to have both of you, and this is an experiment I was very much looking forward to host the both of you, but it totally makes sense once our audience learns what projects we are talking about, because first we are focusing on a project that you, Carmen, are very involved with, and that is the project MEFKON. And obviously, this is an acronym, and it stands for Measurement-Based Improvement of Humidity Forecasting for Contrail Prevention. What is this project about? What is the problem that you're trying to solve here, Carmen?
Well, the main problem we have right now when we do the prediction of contrails is that we don't really have measurements, lots of in situ measurements at the heights where the contrails form, especially of humidity, but also temperature. And when you do a prediction, the input variables are very important. So this project is looking at in situ measurements, or we are trying to use in situ measurements that can be available more or less easily to put them into the predictions, and with this to improve the forecast of contrails and ice supersaturated areas.
Okay, so essentially we're trying to get real-world input or real-world raw data to feed into the models.
Exactly.
And probably not some data that is derived from other real-world data.
Yeah, actually, right now there's not even so much derivation done on other real-world data. We are starting with a question mark to answer a question. So right now we are trying to put in real data to answer a question, to start a model. And that's what we're doing. So we are using water vapor measurements, mainly from 9 aircrafts in Europe that are already equipped with a specific sensor for humidity. And we reprogrammed this sensor so it also measures at en route height, which it didn't in the past. And this data is then going into the prediction. That's one of the main goals. But of course, we don't just want to stay there. We want to look at different kind of sensors, because this one sensor that we are using, it's the WVSS2 from the company Flight, or previously Spectra sensors. That sensor is the only one that is currently commercially available to measure on aircraft, at least with this accuracy that it has. But it seems like it's not exactly the perfect accuracy for this height, because the humidity is very low at this height. So what we are doing also in this project is that we do a comparison with different kind of sensors that were equipped on research aircraft of DLR and the University of Mainz, and are comparing these so that in the end we can also tell how much better should a sensor be to get to a better result. Because we can already estimate right now that with the WVSS2 that we are using, hopefully we can improve the forecast, but it will not be the perfect solution.
I'd imagine that an aircraft is already equipped with some kind of humidity sensing, but you mentioned that the concentrations are so low in these cruising altitudes that you need a whole different set of sensors. Is that right?
Usually, an aircraft is not equipped with a sensor to measure humidity. If it would be, that would be amazing for the MET community, especially for ascents and descents, so we get profiles through the atmosphere. But that's not the case. There are just 9 aircraft in Europe that are equipped with such a sensor. The aircraft are all belonging to Lufthansa, and it's a contract between DWD and EUMETNET and the Lufthansa. And then there are a bit over 130 of these sensors installed in North America. And there is another kind of sensor that can measure humidity. It's called the AMDAR sensor, but the accuracy is much lower. And that's something that is not really appropriate for contrail avoidance. And this sensor, as far as I know, is currently also not commercially available, but that's something I'm not totally sure about.
And are these 9 aircraft that are currently equipped with these sensors in Europe, are these also the IAGOS aircraft, or is this a different set of aircraft?
IAGOS is a different set of aircraft. IAGOS so far is a research development, and you cannot just install the humidity sensor from them because it's a whole package measuring a lot of different variables. And also the data is currently not available real time. And that's something that we need for the MET forecast, and also for contrail forecast. We would need data in real time and not just half a day after or day after.
So the sensors within MEFKON, they would provide the data in real time, or how is it then different from the IAGOS data? Because in terms of the number of aircraft, it's the similar order of magnitude, let's say.
That's correct. The number of aircraft is not so much higher than IAGOS, but the area where they fly is different. And in our case, it's really an operational use of data. We have these 9 sensors already installed. We don't develop them. They are commercially available sensors. They have been installed in already for almost 10 years now. And the difference to IAGOS is that we get data real time currently, but also these sensors fly on medium range aircraft, sometimes also short range distances. So we get data mainly over Europe. And with IAGOS, you get data mainly over the Atlantic, for example, in farther away areas.
Of course, we might want to do one step back, at least in the beginning of the episode, and say, okay, everyone knows how important data is, for applying any kind of model, whether it's AI or deterministic models. In this case, we're talking about humidity data. Why is this data, this humidity data, so important for the topic of contrail management?
From the meteorological side, we try to support such avoidance by predicting ice supersaturated areas where you have a high potential for contrails. And you do this by using a normal weather model. You put in data, and then you set limits or afterwards. So you set limits like saying the humidity, and if humidity in a certain area is higher than a certain value, combined with the temperature that it's lower than a certain value, then you have a high risk within this region for ice supersaturation. The important thing is that your starting values are already very close to reality. As I said before, there are very few measurements at that height available at the moment, mainly from weather balloons. And these get started like twice a day at certain points only. So it's important to have good input values at the beginning, so your prediction at the end is as close to the reality as possible. And if you get more accurate predictions, then you can make these limits smaller. So let's say, for example, right now it would be something, I'm not sure about the number, but it would be something like the relative humidity is above 95%, then we expect an ice supersaturated area. If our prediction gets better, we can maybe reduce this to 98%. So the areas get smaller. And so the better your prediction gets, the smaller these areas that should be avoided will be.
And hence, the smaller, if you avoid it, the smaller the fuel penalty, because you can be more targeted.
Yeah, the smaller fuel penalty and the less flights would have to be detoured.
That as well, right? And that brings us to another aspect, which is very important in this. It's scalability.
Currently, it's really the project is to answer the question if you can do anything with the sensors we have right now, because there's quite a debate about if this sensor is usable at all for something like this. And you can see the project as a quick fix project. If it works, if you can use these sensors, it could be a quick fix for the moment. So you could install them on more aircraft, for example, and have an improved forecast. But this will not be the best solution. That's for sure, because you can definitely improve such sensors to have a higher accuracy, and with a higher accuracy, the forecast will become better. These higher accurate sensors are not commercially available right now. So what we're trying to look at is right now, can we do something with the sensors that we have at the moment? And it's true, we just have 9 in Europe right now, and 9 is not a lot. And it doesn't make sense to, on the long run, to look at this at a very small scale. This project problem, the contrails, that's a large scale problem. If we avoid them in a small area, the effect will be very small. So you would have to try to avoid them in a larger area. And for that, probably 9 aircraft will not be enough. It's a very difficult question to answer how many aircraft you would need. However, we are trying with the data that is available within this project to look also at this question. Right now, we are not sure if we can answer it. But there is some more data available from the US, for example. There will become data available from the UK, so they will install new sensors. And we will see if with this other data, we can answer the question, what is kind of the minimum number of sensors that you would need in a certain area to have a real improvement that is really valuable?
To translate this a little bit into my words, I'd say that the work that you're doing within MEFKON is to try to leverage the technology or the hardware that is already out there, and to be able to give real-time or more accurate real-time forecasting of humidity, which would, be, if you compare it to space, would be the downstream part. But then, of course, afterwards, it's a different part, the upstream part, let's say, how you then translate that into the diversions, right? So how you would do the avoidance of one certain region, for example. You could do that in a pre-tactical manner, as we've discussed previously on the podcast. You could do that in a tactical manner with the electronic flight bag and the cockpit, right? But that is the upstream part, let's say. That is how the data is then used, but you're completely focusing on how can we get the prediction better.
Exactly. We are totally on the prediction side and also on the recognition of contrails. So some people, it's in the project, there are other members as well. We have partners from the University of Mainz and from WX Fusion. That's a spin-off of DLR. And they are looking also at finding contrails in satellite data and matching them with our predictions. So to see where there are contrails in areas where it was predicted. And what WX Fusion is also doing, they want to develop maps to show which regions are climate sensitive in the sense of contrails, for example. So that could be displayed for pilots, for example. So they could see this is an area with a high risk. But that's something that WX Fusion is doing in the project. So DWD is really just looking at the predictions. That's our job. We are meteorologists. We don't do routing of aircrafts or anything.
Well, shout out to Caroline and Arnold from WX Fusion at this stage. Yeah, another point that I wanted to cover is basically following up of one of the previous episodes where we had Peter de Bock on, who is a director of ARPA-E, and they have a section on the pre-trails projects. And these are essentially, what I learned in that episode, are moonshot kind of projects where, you have several teams or consortia competing against each other and trying to come up with a very advanced kind of technology to do the diversions and they are also part of that tool chain is also to develop hardware. Is the approach that MEFKON takes entirely different from that, or are there also similarities?
I think the main difference is that we are, as I said before, more looking at this quick fix, something that we can do right now. These sensors are available right now. They are installed on aircraft, for example, in the US. There are many more than in Europe. So if these sensors are any good to improve the predictions, the changes could be done very quick and for now. But on the long run, it's important to have better sensors, higher accuracy. With that, we will get much better predictions. So I think the ARPA-E project is very important, that if they will develop within this project new sensors, that will be something very important. But it's more in the long run, because they first have to be developed and they have to be produced and installed, and that's a long process. So within MEFKON, we are trying to use what is available right now to make changes quick. And then on the long run, hopefully these other projects will help.
So quick changes, which hopefully help in the long run. Where do we stand in the project timeline?
So now we are 1 year into the project. And to show you the quick changes, we started to reprogram these sensors about the end of last year. And now all 9 aircraft are reprogrammed and are already producing data. So we are getting data from all 9 aircraft. And that's something relatively fast. It actually takes a bit longer than it would need, because we have to wait until the aircraft go into maintenance. You just don't just take an aircraft out of the operation just to install a new software, right? But it's a change that can be done within half a year, for example, while developing a new sensor or installing a new sensor takes much longer. So we are now 1 year down into the project. The data is now available. It just started recently that we got the data from the 9th aircraft. The weather forecasting experiments, they are developed, so they have to be run now, but the concepts are there. And also the work on the satellite data has started, that the University of Mainz and WX Fusion is doing.
Great. Those are some amazing milestones already. And now I want to be unconventional and ask you, is there anything I should have asked more about MEFKON? Is there any aspect that we should cover?
I think that what is important to say is that there are a lot of different projects out there, and each of these projects is important, but the most important is that we all work together, and that is working pretty well right now, I feel, in this community. We had a nice workshop on water vapor measurements on aircraft, for example, in December in Offenbach. And after that, a lot of new connections started, and we are exchanging between different projects, talking to members from different fields. And that's very important, because every single project will help. And only if you look at the results all together, you can really make a change. And it's very important that we work together, the Met services, but also the aviation industry. It's OEMs that would have to prepare to install such sensors, for example, but also airlines and ANSPs and so on. Only if we all work together, it works. And I have a good feeling here that we can make a change, because there's a lot of collaboration right now.
That was a very motivational kind of a speech, and I can only agree. And I also think that every kind of scientific insights or progress is a step forward, even if maybe, you know, the result could be that we are off by some factors, but maybe this at least increases the certainty that we are not off by a smaller factor, right? I think that has happened with a couple of previous studies, and we should be happy that you know, the potential of these persistent warming contrails, the negative impact it could have is huge. So if we can just increase the certainty in how huge it is, that already helps, even if sometimes it means that the initial estimate overshot a little bit, you know, the reality. But I think all in all, the whole ecosystem is definitely advancing. So thanks, Carmen, already for these insights on MEFKON. And one event that I have in mind, which also fostered the collaboration in the ecosystem, was this event by Eurocontrol in Canso in last November. I saw a presentation of Björn's there, which was very insightful. And today, yeah, we want to follow up on that. What is the project about, and what are the goals?
Yes, thank you very much. D-KULT is also like MEFKON, is a project within the German Federal Aviation Research Program. And you say it already, as it calls demonstrate climate and environmentally friendly air transportation. And the aim or the objective of this project is to create a feasibility study of the climate optimized flight trajectories, planning due to avoidance of persistent contrails or contrail cirrus clouds in ice supersaturated areas. And the evaluation of persistent contrail generated will be carried out by satellite observations. Yes, and in this project we have much more partners than in the MEFKON. As a partner covers the entire spectrum of aviation, as a range from the air traffic control, airlines, system houses, aircraft manufacturers, research institutes, then the weather service DWD, and also aviation associations to the aviation industry. But so MEFKON is led by DWD, however, the D-KULT is not led by DWD. DWD is only partner. The D-KULT project is led by the DLR Institute. That's important to say. Yes, in the time frame, the time period of the D-KULT project, it's a 3-year running project, and it started in June 2022 and will run until June 2025. So that means 2 years are over, and we have 1 year for our remaining time. Yeah, what we are doing, we have developed meteorological forecast input parameters for the tools to calculate the climate impact of non-CO2 effects. The meteorological forecast input parameters are coming from DWD, and these climate impact tools or algorithms are coming for the non-CO2 effects are coming are supported by or provided by the DLR. Yes, in the climate and the meteorological input data as well as the ice supersaturation in form, what we call it here in the project, potential persistent contrail, and the climate impact based on algorithms and tools will be made available to the aviation users in the project in the so-called experimental data sets. So, and therefore the DWD uses its global numerical weather prediction model called ICAN to forecast all these meteorological input parameters. For the climate impact tools, like these algorithmic climate change functions, these ACCF or these COSIP tools, which are coming from the DLR, and also for the potential persistent contrail, like these ice supersaturation areas. So in the prediction of the relative humidity, this ice supersaturation is subject to large uncertainties compared to all the other input parameters you need or require for these input tools like COSIP or this algorithmic climate change functions. So about 15 different met input parameters. So in the one parameters with the highest, much highest uncertainties compared to the other parameters is the relative humidity with supersaturation. So in the DWD is therefore working to improve this parameter. That's our intention, to improve these parameters to get a better forecast finally of this ISSR or of the climate impact of the contrail.
So to Björn, to remain first on a higher level, I think what I understand is that this project is unique in the sense that it tries to go end to end. Right, so that's why it's such a huge consortium, including also air traffic management, but also airlines. And of course, many studies have been done previously, which have been simulation only, but this one conducts real-world flight tests. So there will be actual flights, sort of like in an A/B test, right? There will be actual flights who will be diverted. What scale are we talking about? How many actual real-world flights will be diverted?
Yes, okay. First, the DWD is working on improving the humidity forecast. Yes, on the parameterization of cloud microphysics, as it's called the two-moment scheme, and so we set up a special experiment of the ICAN prediction model with this two-moment scheme, and we set up also ensemble predictions in order to estimate the uncertainty. So that was now our work, and now we provide these data sets could provide these data sets to the aviation users. Yes, and you are right. The advantage of this project is that all kind of aviation users attend this project consortium. It's not only focused on meteorological improvement, or it's not only focused on what could do aviation users. We are looking to the complete chain, to the complete process from the developing of meteorological forecast to the testing of flight test together with airline and the ENSPs. Yes, and you are right. The climate optimized flying should be that's now started. Is to be tested in a 100 flight trial, and that's also in collaboration with the German government's climate neutral aviation working group. And the test region is Europe.
The test region is Europe. Okay, so also quite huge, and according to recent studies, also a region which we should try to fix with a higher priority than maybe others.
Yes, Europe and a little bit North Atlantic, but the main region is Europe. So in addition to Lufthansa, the DHL and Condor are also participating in the trial with some data supply via the Lufthansa systems.
Right. Okay. As this is an end-to-end kind of a project, there are so many aspects we could cover, and I promise you, I'm also trying on interviewing other people from the consortium. But since you are here representing the DWD, I want to drill down just in one aspect that you mentioned. You mentioned that you're especially working on the parameterization. Now this might be, new terms for some of the audience, and you're using a two-moment scheme here. And ensemble predictions, as far as I understand, is basically a set of predictions with different initial parameters, right? And then you look at the aggregate, or you look at the average afterwards.
Yes, ensemble prediction are generated in order to estimate the uncertainty in the prediction, especially in the humidity. And for this purpose, it's correct, the initial state of the atmosphere is varied. It's the start of the model initiation. The point is, that could be coming back was Carmen told us or explained us, we have not at every point on the Earth's observations and measurements. The initial state of the atmosphere is described with an uncertainty, and so that means the model initiate is starting on an uncertainty state of initiation, and the model result, the forecast, depends on the atmospheric initiation. Yeah, that these are non-linear equations, the forecast equations of numerical prediction models are non-linear, and that means the results depends on the initiation. And if I vary the initiation a little bit, then the result, the forecast, could also varying. So, and due to that, we were not able to describe the initiate state of the atmosphere completely correct, because we have not every meter or every kilometer in observation. We could be happy if there's flying 9 aircraft, or there's some satellite, or that we have some satellite observations, and some. So that means it's not possible. Will never possible to describe the initial state of the atmosphere completely correctly, and that means the forecast will every time depends on the initial state of the atmosphere. And that's the reason why then, yes, our colleagues from the R&D department are varying the initial state of the atmosphere and calculating the forecast 40 times. They are running the model 40 times, and then they receive 40 results of the forecast due to 40 initial states of the atmosphere. And thus, it will be possible to estimate the forecast and uncertainties, the forecast spread at the end. And the forecast spread will diverge with increasing forecast time. In the beginning of the forecast, the spread is quite small, and after forecast time of 2 days, the spread is increasing more and more. Yes, that makes sense. And that's the reason why DWD, or why we are also calculating this ensemble forecast in order to have an impression about the forecast and uncertainty, especially for the humidity.
And you mentioned that, parameterization is just a term for researchers, this might be horrible right now because we can't dive into all of the aspects, but just in my language, what I learned is the parameterization is essentially these effects which are dominating, the behavior of contrail formation are happening on a much smaller scale or on a much smaller grid than, we have the weather data that is, whether it's observed or even predicted. And the parameterization is the, let's say, approach to get on a subgrid level these forecasts. And one thing I've learned, because we had Adam Durant from Satavia on the podcast before, is that another way to tackle this is to take off-the-shelf weather models such as the WRF model and edit the parameterization in such a way, they're using the Thomson microphysics schema in such a way that it's very beneficial or very good at predicting ISSRs. You've mentioned the ICON model. Now, are those on the same level, and how do these approaches compare to each other?
The ICON model is our numerical weather prediction model with a grid resolution of 13 on a global scale, 13 kilometer. The DWD is at the moment not processing, or is not working on a post-processing, but you're right. Some processes like this humidity forecast need some parameterization, because the scale of this 13 kilometers is too large, and that's why the numerical or the AMDAR colleagues are working with these parameterizations. Our main topics at DWD these are where we are working on this parameterization of the cloud microphysics, now here in the form of this two-moment scheme. And the other main topic will be to improve our data assimilation scheme in order to integrate more data, not only the airborne water vapor observations, also to include more satellite observations and LiDAR observations. So these both issues, we are working on it to improve the humidity forecast within our NWP prediction models.
And from your perspective or your role within the project, what is the next milestone that you're currently working towards, you as contributing to the weather prediction aspect of the project?
The next one, the parameterization of the two-moment scheme, that's now done in this research project, the D-KULT. So the next step will be the operationalization. That will also take some time. And the next point will be that we will work or have more focus on the data assimilation.
Okay.
To improve the data assimilation with more data like satellite data, with a new satellite generation, like this MTG, this Meteosat third generation, and other satellites on the same quality.
We are all very excited for those results, so keep pushing it. And someone else who was very excited about these activities that are going on is our previous guest, Jeremy Thompson, who was representing the pilots' perspective, as he is from the British Airline Pilots Association, and he passed on a question to you. What can airlines offer in terms of data back to the researchers for example, humidity sensing on the aircraft or on routine flights?
It's a question that I can take. So there is the question, who pays for these measurements and the installation of sensors? And it's not exactly cheap to install such the humidity sensors, and they don't come factory built in at the moment. It might come in the future, but right now it's not available. So far, all these installations in the US, but also in Europe, were paid by Met Services. But the funding here is very limited. That's why there hasn't been a development for a long time. And the scale at which we would need these sensors is not very realistic that this will be paid by Met Services in the future, especially because this is not our main responsibility. It's actually not our responsibility in the first case at all, because we do predictions, and for regular predictions, we don't necessarily need these measurements at this height. So what can airlines do? They could actually contribute to such developments and even be available to have sensors installed on the aircraft. So far, even recently, it was very difficult for some colleagues of us from other Met Services to find airlines that were willing to install sensors even when the Met Service paid for the entire installation. So something that airlines can do is being open to these measurements on one side, but also think about funding, because this is something that will impact the airlines in the end. They need good predictions to not have very high costs due to contrail avoidance.
Right. And because you are two guests here for the first time, I also had two questions for the first time that were passed on. Another one is from Jo Dardenne from Transport and Environment, who was here a couple of episodes ago. And she asked you the following question. If you were policymakers, which policies would you put in place to help move contrail management forward?
Yes, it was also my answer or statement at the ECAG Environmental Forum. Yes, we are providing our meteorological input data for these climate impact tools. So these are about 15 input parameters which are required by these climate impact tools. And as I told, so especially this humidity, this ice supersaturation or the supersaturation has a relatively high uncertainty. And our work is to give the users some information how they could handle with this uncertainty. So that's why we are also working, providing the ensembles in order to give the information of the uncertainty spread, or how they could handle with the uncertainty, so that we give a recommendation that they could maybe how they could work with with probabilities based on the different ensembles. So that's our work. That we are saying that we say, oh, we don't know how is the uncertainty. We would like to find ways how we could handle with this meteorological forecast uncertainty. That's our and I see and there is these people, the auditorium at this ECAG Environmental Forum was quite happy. That was this was a very general question on an issue. Okay, we would like to include or to make this MR3 system next year in 2025 operational, but we see there are a lot of uncertainties. But nevertheless, we will start. We have to start. But how we could handle with these uncertainties, and the meteorological forecast is only one uncertainty in the complete process, I think.
Thanks for that response, Björn. And of course, you also have the chance to pass on a question. And our next guest is Professor Manuel Soler from the Charles III University of Madrid.
I would like to ask him if he has an idea on how neural networks, or if artificial neural networks could help in the assessment of water vapor measurements in some way.
Great. That's a great one. I'm happy to take that on. And this concludes our episode today. It was the first time we had two guests, and I'm really happy we did it. I'm really happy that I had the honor of hosting two experts for the German Weather Service, and particularly with those two projects that you're focusing on. So Carmen, Björn, thank you very much for being my guests.
Thank you very much. It was great being here.
Yes, thank you very much. It was very great to be your guest.
Thanks both of you, and speak soon.
Bye.
Bye.
Bye-bye.